Welcome to tutorial on circuit theory, and today we're here to discuss on the current division rule. Okay, so like you all had noticed in our previous tutorial on voltage division, or rather voltage divider rule, we had previously told you that of course voltage divides itself when apply a voltage source in a circuit. Similarly, if you would consider that for a current, it happens over there as well. Okay, so that's how we can just frame a generalized rule known as current division rule, with which we can just find out the current in that divides into the various branches of an electrical circuit. So just for the moment, consider the circuit over here that's got a DC voltage source connected over here, and there's this series resistance resistor over here, known as denoted with the symbol R, and there we go, we have a parallel branch, okay, with two resistors, namely R1 and R2, connected. Okay, so we're basically interested in studying how the current divide itself when it just moves on to various branches. Okay, so let's just for the moment consider that in this circuit, okay, so there is obviously a net current, okay, I, that should be flowing. All right, so we just denote that net current over here with the symbol I. Okay, so this particular voltage source, okay, here outputs this current I that passes through this series resistor R, and then when it reaches these points, okay, I'll just use the red color so that it'll be visible in a better way. Okay, so there you go. So when it reaches these red points over here, let's just call them X and Y points. Okay, so when this current I, that is obviously flowing through these yellow colored wires over here, and it then reaches this point X over here, it'll just basically tend to enter, and basically divide and enter into each of the resistors R1 and R2. Okay, so we're basically dealing with this division of the current into the two branches. Okay, let's just for the moment consider that the amount of current that should enter through this resistor, this parallel resistor R1, be let's just call that I1, and then the other part of the current that should pass through this parallel resistor R2 over here, let's just call that I2. No problem. Okay, so so we know that the current basically divides at these points whenever it encounters parallel branches of resistors, or rather other kinds of circuit elements as well. But how does the current divide? So that's what we're exactly trying to find over here. So if we need to just basically find the magnitude of these divided components of the original current that passes through the circuit, then we obviously need to use the current division rule. Okay, so here we'd be basically dealing with the parallel part of the circuit. So as a result, I'm just going to modify this figure over here. There you go. On the right we have the modified figure. As I said, that will be basically dealing with the parallel part of the circuit, okay, where we have the parallel resistors R1 and R2 respectively. So we've just extracted that part out over here. So as I was saying that, these two are the points X and Y respectively. Okay, so let me just label them over here, so in order to avoid all sorts of confusion. And there's this current I entering into this parallel branch and dividing itself into two parts, known as I1 that passes through the resistor R1, and the other one known as I2 that passes through the resistor R2. Alright, so there we go, we have our model. And now here we'll be basically applying the current division rule in order to find that. Okay, so we know that whenever this current would basically pass through this parallel part of the circuit over here, it would obviously have a sort of parallel voltage across, that will basically develop across this parallel branch of resistors. Okay, that would obviously be a part of this total voltage supplied by the source. So let's just for the moment consider that this parallel voltage that would occur across these parallel resistors be denoted by the symbol V parallel over here. Fine. So with that, if we just keeping that in mind, if we just try to find it out over here, then first of all we need to determine the equivalent resistance of this parallel resistors connected over here. Okay, so that'll be given by, I'll just write down over here, R equivalent equals to, well, R1 multiplied by R2 divided by the sum of the resistors magnitudes R1 and R2 respectively. So that's the equivalent resistance offered by this parallel combination of the resistors R1 and R2. Okay, so now the total voltage that's pointed out over here, that will be a V parallel that will basically develop across this parallel connection of resistors, would be obtained by multiplying the equivalent resistance of this parallel network formed by the resistors R1 and R2 and the net current I present in the circuit. Okay, so we can basically write it down as R equivalent multiplied by I. Okay, and now we obviously know that, well, in case of parallel connection, the net voltage drop occurring across the parallel network, okay, falls across each of the resistors present in the network as well. So here, as we can see, that V parallel is of course the voltage drop occurring across the entire parallel network over here. So this particular voltage, that's voltage drop over here, that's V parallel, would individually occur, or rather fall across that of the resistors R1 and R2 respectively. So if we need to find the value of the current I1 passing through the resistor R1, we can basically obtain that by dividing the parallel voltage, that's V parallel, okay, with that of the resistor R1. Alright, so that way we can just obtain I1 over here. And of course, if we need to find I2, then we can also apply the same procedure to find out I2, as R2 would also have this parallel voltage, that's V parallel, fall across, or rather drop across itself as well, like like that of the resistor R1. Okay, so there we go. Now if we just number these relationships that we obtained over here, as let's say this one be known as, well, relationship number 1, and this one be known as number 2, and over here this one be known as number 3. Fine, so let's just pull down the page a bit. Okay, so now if we need to find the exact value of that of I1, then we need to substituting the value of V parallel that we obtained over here in relationship number 1. So let's just put it. Okay, so putting 1 in 2, we'll get, well, R equivalent multiplied by I divided by that of R1. And now we know that the value of R equivalent is something like this. So if we just go forward and put it over here, okay, so let's just pull off this I and R1 first, and now putting the value of the R equivalent over here, we can just obtain an expression that would look something like this. So we can see that the R1 and R1 cancels on the numerator and the denominator, and with the result we obtain I multiplied by R2 divided by R1 plus R2. So there you go. So that's the expression for the current through the resistor R1, that's I1 over here. And similarly, we can also obtain I2 in a very similar way. If we just go forward and put the value of V parallel from that of equation 1 in 3, then we can also get the same thing over here. Let's just put it, okay, R equivalent multiplied by I divided by R2, and then go on doing the same procedure over here. Just extract I and R2 and put the value of R equivalent over here. Okay, so there you go. And now we can see that R2 would cancel both in the numerator and the denominator, with the result which we'll obtain over here, and it'll basically look something like I multiplied by R1 divided by R1 plus R2. Okay, so there we go. We found out each of the values of that of I1 and I2 as well. That's the value of the branch currents passing through the resistors R1 and R2 respectively. So in any of your problems, whenever you can see that there's a parallel network and the net current basically divides this way, we can basically, without any hesitation, apply the current division rule in order to obtain each of the, the values of each of the branch currents without a doubt. Okay, so that's just bring us to the end of our tutorial discussion on the current division rule. Hope you've enjoyed it. Don't forget to watch our next tutorials on circuit theory as well. So till then, it'll just be a short goodbye for now, and thanks for watching.